Okay, maybe we should start. Start on time. Yeah. Thomas, you
Yes.
go ahead.
Yeah. Welcome everybody to this episode of the DMFT Quantum Embedding Online Symposium. It's a great pleasure to introduce you two speakers on actually a very similar or even the same topic, namely twisted bilayer graphene, and we are all very much looking forward to a talk. So just for organizational purposes, if you have a question, you can raise the hand with the raise hand option, or you can also type the question into the chat, which Olivier and I will be constantly monitoring. And I also have to say best greetings from Antoine. He unfortunately cannot join today because he's giving a talk himself at this very time. So the first talk is given by María José Calderón from the Instituto de Ciencia de Materiales de Madrid. And the title of her talk is The Unconventional Normal State of Twisted Bilayer Graphene. Maria, we're looking forward to the talk.
Okay, well, thank you so much. First of all, thank you for organizing this seminar series, which is very interesting, and also for inviting me to give a talk here. It's a pleasure and an honor to address this community and tell you about our work that we have been doing for a while already. So we have been looking at the unconventional normal state of twisted bilayer graphene, and we will see what we mean by that. And the first thing is to present my collaborators. Anoushri Datta, she's now in France, but she was a postdoc in our group until 1 year ago. Alberto Camjayi from the University of Buenos Aires in Argentina. And then, Lenny Vascones, who is a long-term collaborator in many other topics as well. So let me start just by presenting twisted bilayer graphene that you all know. So this material and other related van der Waals heterostructures have become in the last few years a great playground to study condensed matter condensed matter physics. No, you can rotate one of the graphene layers on top of the other, and then a superstructure is formed, this moire pattern with a very large unit cell. So this very large unit cell has thousands of atoms, and that means that we have a very small real zone. Okay, so we have a lot of folding of our bands, and this added to the fact that we have the tunneling between the two layers. This gives rise to this kind of bands in which we have flat bands that are separated from the remote bands, and these flat bands are of the order of a few milli-electron volts, and we have these two bands per valley and per spin. So we have one valley that comes from the K points of the graphene layers, and the other that comes from the K prime points. So we have this degeneracy. Well, it's not really degeneracy. We have the black lines, the black curves are for one of the valleys, and the red ones for the other valley. And we also have the spin degeneracy. So in total, we can have up to 8 electrons here. So the charge neutrality point is at the Dirac touching that is protected by symmetry. So we keep the Dirac touching that we have in the single layer of graphene. And then we can dope from -4 to 4. So we can dope with electrons and holes with respect to the charge neutrality point. So these very flat bands that we see here imply that the electron-electron interactions are relatively very important in these materials, and in fact many correlated states have been observed in this system. These include the existence of these insulating states at integer fillings of these flat bands. We have also superconductivity at intermediate fillings. Also some cascades, and this spectral weight reorganization of integer fillings has been observed. And then many symmetry broken states like intervalley coherent states, ferromagnetism, integer quantum Hall effect, fractional Chern insulators, charge density wave, etc. And this happen at low temperatures, and we will see that other features survive up to higher temperatures. So the effect of correlations were studied very soon, already in 2019. There were some hints of the importance of correlations with STM measurements, in which you could see that when you dope, there is not a rigid band shift of the bands, but a reorganization. So here, I show a plot from this paper in which they measure the DIDV, which is proportional to the density of states for fully occupied flat bands. And we see the two peaks here. And if you are at intermediate filling with partially occupied flat bands, we have a completely different reorganization of the spectral weight. Also, it was observed that this DIDV as a function of the filling, this is a gate that you can apply to change the filling of the flat bands, and you see that there is a suppression of this density of states every time that you hit an integer filling of the bands. Later in 2020, these beautiful experiments and other related ones showed that there is a strong reorganization of the spectral weight that you can see here. So here in horizontal is a bias voltage that allows you to explore from zero, which is the chemical potential. You can explore the spectrum, the energies of the bands, and in perpendicular, in vertical, we have the gate voltage that allows you to change the filling of the bands, the doping. And we can see that there is a spectral weight reorganization with resets at integer filling. So we have these periodic resets. And there is like this change in the spectral weight that look like cascades. Then we also see a different behavior at the charge neutrality point. And here we can see also the oscillations of the remote bands. These two plots correspond to putting the STM tip in different areas of the twisted bilayer graphene. So this would correspond, the left one, to areas in which there is a stacking of AA, so an AA stacking of the graphene layers, and here it is where you have the AB stacking. Okay, so you see some different features. These were measured at 6 Kelvin, but you can see similar features, that these features can survive up to tenths of Kelvin. Another set of experiments that showed that there are these spectral reorganizations and the correlation with the integer fillings is in the inverse compressibility, that also show the same kind of information. So you can see that there are asymmetric sawtooth peaks that reset at integer fillings, and then a symmetric peak at the charge neutrality point. And as well, these features survive up to tenths of Kelvin. So these are temperatures at which we don't expect to have all the symmetry broken states that are more prevalent at lower temperatures. Finally, just to finish with the experiments that I want to focus on later when I show the results. The resistivity at integer fillings that I mentioned before has also been observed at to high temperatures. So these experiments went up to 40 Kelvin, and you can see that there are these features that arise. So this an increase of resistivity at integer fillings. In particular, I want to point out these ones that are more clear. So you can see that the resistivity is increasing, is large, even at high temperatures, and it doesn't seem to go away as you would expect if it went to a non-interacting picture. Okay, so the focus of our work has been to find out the relation between these observations and electronic correlations at temperatures at which we don't expect to have symmetry broken states. This is the question that we wanted to answer, and then I want to stress that our focus is to study this normal state. So we still expect that there are at low temperature, there are broken symmetry states, but we are not focusing on that. This I guess that it will be the topic of Gautam in the next talk. But we are focusing on this normal state, no? This normal state from which all these low symmetry states are going to arise. But here we don't have these broken symmetry states, just the effect of correlations between by itself, no, without provoking broken symmetry states. Okay, so the approach that we want to do is we use a mixed approach with dynamical mean field theory and Hartree. I will explain how. And in order to do this, we need a suitable tight binding model for the Moiré lattice. So let's start by presenting the model. It is well known that due to the topology of the flat bands, we don't have a model for only the flat bands with Vannier states. So we need to include more bands. We need to include the remote bands. So there are a few proposals that have been made for this. We have chosen this particular one proposed by Carr and collaborators, in which we use an 8 orbital model for the Moiré lattice. This allows us to keep all the important symmetries of the system, like the C2T, C3, and the mirror symmetry. So in the plot, you can see the black lines that are coming from a continuum model. We have chosen a rotation angle of 1.08, that is very close to the magic angle 1.11. And the blue lines is the fitting that we can do with this 8 orbital model. So these are the locations of the orbital models, a sketch of the orbitals that we use. So we have a triangular lattice that is signaled by these red and orange points. And here, these are the correspond to the AA stacking. And here we have 3 orbitals, 2 with P plus and P minus symmetry, and 1 with S symmetry. Then in the hexagonal points, we have these green orbitals that have PZ symmetry, and these correspond to the positions in the lattice in which we have AB or VA stacking. And then in between, we have these domain wall regions that are signaled here in purple, and here we have 3, this is a Kagome lattice, and we have 3 orbitals with S symmetry. So these are the orbitals that we have, and then we can have a look at what is the orbital weight of each kind of orbitals in our bands. And here I have made 2 groups. One is with the AAP orbitals. These are the orbitals that are in the triangular lattice. And the red color here and the width of these bands is related to how much, what is the weight of these orbitals in these particular bands. So we can see that the AAP orbitals dominate mainly the flat bands, except at gamma, while the rest of the orbitals that we will see that we would call them LC because they are less correlated, dominate the remote bands, except at gamma, where they are also important in the flat bands. So with these Vannier orbitals, we can also calculate the interactions doing the integrals, and then I plot here the density-density interactions as a function of the distance between the orbitals. So at 0, we have the on-site interactions. And we see that very far away, we still have significant interactions. We cannot throw them away. And I want to distinguish what happens with the 2 types of orbitals that we have. On one hand, we have the AAP orbitals that, as I said, dominate the flat band. So they have a very narrow bandwidth, and they have the largest interaction. Okay. And on the other hand, the other orbitals have a smaller interaction, but it's not really something negligible, so we cannot ignore them. And we also have, as I said, all this long tail of interactions that are very similar, so we have to include them all. But the thing is that we have like 2 sets of orbitals, ones that we expect to be very strongly correlated, and others that we expect to be less correlated. Okay, so then that makes us think about a heavy fermion picture in which we have some orbitals that are going to form local moments, and the others are screening these local moments. And the idea then is to use this to make a suitable approximation to solve the problem. And what we do is that we consider at the dynamical mean field theory level only the local interaction, the on-site interaction between the AAP orbitals. And we do the self-consistency here using this impurity solver in continuous time quantum Monte Carlo by Howlett. And then the rest of the interactions, these are all the other interactions between the AAP, within the LC orbital section, and also between AAP and LC. They are all considered at the Hartree level, and we do self-consistency here as well, okay? And importantly, we don't allow symmetry breaking to occur so that we can get an idea of what happens without symmetry breaking. Okay, so in all this, I'm introducing the density-density interactions. I'm not taking into account exchange and other terms that are smaller. They can be important for symmetry breaking, but here we are not taking them into account. Okay, so let's go to the results. Just a note that I'm going to focus here on results for a temperature of 6 Kelvin. And I'm going to show results for two sets of parameters. The qualitative results are very, very similar, but I have these two sets just because of the way that we have been performing the calculations. So, but you will see that they are all consistent. So this ratio first that I didn't introduce, this omega naught divided by omega 1 is just the ratio between the tunneling at the AA stacking points compared to the AB positions. And this value is different from 1 because we have relaxation. That is also behind the fact that the flat bands are isolated from the remote bands. So before going to the result, just remember a little what we were seeing before, that these cascades that have been observed in STM measurements, in which I remind you there is a spectral weight reorganization, resets at the integers, different behavior at the charge neutrality point, and the oscillations of the remote bands. And these results in which the density of states has been seen to to be depressed at integer fillings. And this is the results that we get out of our DMFT plus Hartree calculations. So this is the density of states, which would be proportional to the DI/DB characteristics that have been observed experimentally. And we observe exactly the same kind of things that have been observed in experiments. We have this spectral weight shift from energies of the order of where you would expect to have Haber bands towards the chemical potential, which is at 0. And then every time that we fill the bands with an integer value of electrons, we have a reset of this spectral weight reorganization. We also see this different behavior at the charge neutrality point. And here we see the oscillations of the remote bands. Okay, these oscillations of the remote bands are coming from a part that I forgot to mention before, but there is a part in the remote band that is very flat. So this is giving us this strong signal at higher energies. Of course, we can also plot the density of states at the chemical potential as a function of the filling. This would be the charge neutrality point. Here we are plotting, we are doping with electrons. Here we are doping with holes. And we see this suppression at the integer fillings, akin to the one that has been observed experimentally. We can also calculate the inverse compressibility. There is a derivative of the chemical potential with respect to the integer filling. We have defined the chemical potential from the bottom of the lowest of our bands. And we see these asymmetric peaks that happen in this sawtooth peaks in the inverse compressibility, the symmetric one at the charge neutrality point. And this is very similar, remember, to the experimental result that I showed before. We can understand a little how these things happen if we look at the filling of the two sets of orbitals, no? These AAP orbitals, which are the strong correlated ones, and the less correlated ones, the fillings that are dominating the remote bands, no? And we can see that most of the filling goes to the most correlated orbital. So the scale here in vertical, it goes from -4 to 4, while the other orbitals are filling, I mean, the change in the filling is smaller as we dope. This scale is much smaller. We see that for the AAP orbitals, the increase of the filling as we change the doping is monotonous, and there's a very slight step at interior fillings. And in the less correlated orbitals, we have a non-monotonous increase of the filling. So we see that the moment that we go from one interior filling to the next, we first have like a fast filling of these less correlated orbitals, and then the filling gets like a constant with doping, and this means that the filling is happening basically in the AAP, and we will see how this is seen later in the bands. Okay, so just to finish the comparison with the experimental result that I presented at the beginning, I remind you of these resistivity measurements as a function of the doping, and we can see how these resistive states survive up to high temperatures at interior fillings, and we have calculated the DC conductivity that follows this kind of behavior with a suppression of the conductivity or an increase of the resistivity at the interior fillings. No, that is similar to the result that we have if we look at the density of states. So we can learn much more by looking at the bands. So these are the bands at the charge neutrality point. We see that here, remember that the AAP orbitals dominate this part of the flat bands, and here they are becoming incoherent, so their spectral weight is shifting to the Hubbard bands, and this is what we see here. So we see this incoherence because of the formation of the local moments from the electrons coming from these orbitals, but we have a momentum selective incoherence because at gamma the spectral weight is dominated by the less correlated orbitals, and they are coherent. Okay, so we have a different presence of incoherence as a function of the momentum, and this is just a reflection of these two kind of electrons. If we start doping, we see that the electrons remember that the electrons start to fill the LC orbitals. So the AAP ones still are very incoherent. And there is here a change in the on-site energies. So here we see this band bending that is coming from the Hartree results, in fact. Okay, so we have a different behavior of the two orbitals, no? Because they are filling differently as we dope. And then as you keep increasing the doping towards the next integer, you see how the heavy quasi-particle forms, and there is a band flattening. And then if you keep increasing above 1, then everything starts again, right? Like all this change in the role of the different orbitals and having the more incoherence or less incoherence depending on the filling that you have between two integer fillings. We can also look at what is happening by plotting the spectral weight as a function of doping at particular values of the moment of k. So at gamma here, this would be this part. Here we are plotting at gamma for different nu and for different fillings and for different energies, and we can see well, the signals of the flat bands. These are the two flat bands that have this strong coherent peaks here, or signals here. So these are the two flat bands, and then we have this part of the remote band, the one that is closest to the flat bands, that are giving us this signal with these oscillations that we have seen already a few times. And this bottom plot would correspond to the M point. Okay, so here in particular at the charge neutrality point 0, here you don't have much of a signal, but then remember that at the 0, at the charge, at the chemical potential, sorry, there is a quasi-particle peak forming, and you can see, if you look at the M point here, you can see how this quasi-particle peak emerges and how it disappears again and then it emerges again, etc. And the thing is that all these, I mean, we can get from the experiments, but it would be great to see this. Sorry, we can see this from the theory, but it would be great to see it also in experiments, and the measurement that can be done in order to explore these features that I have been explaining is to measure optical conductivity. So this is what we see here. This is the filling. So this is again the charge neutrality point, and this is the energy. So we can see that the optical conductivity has strong features happening at a range of energies that are given by the transitions between the flat and the remote bands. We have stronger peaks in these positions or these fillings at which we have a well-formed quasi-particle peak. And we have broader signals where there is more incoherence. Okay, and we can see also the resets and all these features that we can see very clearly in the density of states or the DIDV from the STM measurements. But here we have like another probe to see what is happening, and we hope that this kind of results can help us elucidate whether in the experiments we have these kind of features that we have observed. And just before finishing, just mention the consistency with other work. So there is this work by Hoffman et al. In 2022, in which they did some determinant quantum Monte Carlo, and this would be what they get for the flat bands at the charge neutrality point, which is very similar to the result that we have got at the charge neutrality point. And also, the work that Gautam will present in the next talk, in which they have done very similar calculation, but based on a different model and also using a different impurity solver. So the results are all consistent. So the density of states, the bands, the inverse compressibility are all consistent in the case that we have studied here, the symmetric state, but they also have studied the broken symmetry states, and as they will show later. Okay, so with this I finish. Just to summarize, this DMFT plus Hartree calculations of the 8 orbital model in the normal state, so without symmetry breaking, allows us to find out the transitions that have been observed in STM experiments, the asymmetric peaks here in the inverse compressibility, the resistive states at interior fillings, and also we have seen that we should expect to have a momentum selective incoherence, and that we could study all this by looking at the optical conductivity. Okay, so with all this, I thank you for your attention.
Thank you very much, Maria, for this fascinating talk. I'm sure there are a lot of questions in the audience. And again, as a reminder, you can use your raise hand feature. Yeah, Andy.
Hi. Yeah, beautiful talk. I will ask this question also to the next speaker. But I couldn't quite follow, do the flat bands in your calculation, as you change doping, do the flat bands sink into the weakly correlated bands or not? In
Yeah,
other words, is there a doping in which I have in which I really have a weakly correlated band at the Fermi surface?
What you have here, maybe I can zoom here. This part, I mean, it's not really that it sinks in, but this is coming from the less correlated orbitals that were already there without interactions.
Yeah. Right. No, but so that, I think that answers my question, that in your calculation, perhaps in contrast to what I heard about the other calculation, basically the weakly correlated bands stay separate, and this rearrangement with the oscillations in the compressibility, et cetera, is a property of essentially playing games only with the flat bands.
Yeah, but I mean, yeah, we have a deformation of the heart at the heart tree level.
Sure.
We have a deformation of the bands, and this is what is going basically to show up here. So if we look at, we look at here as well.
Mm-hmm.
You can see that this shape is coming from a heart tree level.
Sure. Understood. But this I'm asking because in.
But this changes at interior feeding. Okay, so this at interior feeding you have a change here, which is not at the heart tree level.
Mm-hmm. Right. Got it. Thank you. No, I'm asking because this relates to the vexed question of double counting correction in the whole DFT plus DMFT theory more broadly. Because what the double counting correction really does is position the correlated bands with respect to the uncorrelated bands.
Yeah. Mm-hmm.
Anyway, but thank you very much. That answers my question. That's very interesting. Thanks.
Okay. Thank you.
Thank you. And Gautam already knows which question is to be answered in the next talk.
He probably knew it already, but yes.
Any more questions?
But I mean, seriously, I think that also from an experimental point of view, it's an interesting question: does it happen or not, and what is the right spectroscopy to see if it happens? Anyway.
Any more questions from the audience at this point? So I would have one more question, namely about the significance of the negative inverse compressibility. Can you comment on this? Because they were negative values as well.
It's not. I mean, it's not this inverse compressibility that that appears in the experiment and that we also have here. It's not related with interface separation or anything like that. It's related because you have a capacitive coupling to the gates. And in fact, in order to mimic this thing that you have in experiments and you cannot get rid of, we have mimicked it by measuring our chemical potential or the change in the chemical potential with respect to the bottom of the lowest band that we have. I mean, this is the way that we find out or that we thought that was that make some sense in order to be able to have these kind of features that were observed experimentally. But it's not it wouldn't imply a phase separation or anything like that, because it's related to something of the setup, let's say.
Thank you. Maybe a quick other question. So did I see? No, there is nothing in the chat. Sorry. No. So for your interaction parameters, was this a CRPA calculation which you did there, or how did you? So for the interaction parameters of your model, did you do CRPA, or how did you estimate the interaction?
For the interactions? The interactions we we got them from you have the Vanier your Vanier orbitals, and you just calculate the integrals of the overlaps, let's say, of the interactions. So that gives you these parameters, and then what we use is different values of the epsilon of the dielectric constant. to mimic that. Of course, you have an environment. So as I said, that we chose different sets of parameters, but the results are basically the same. The qualitative results are the same.
Mm-hmm. Thank you. So I see no further questions in the chat nor any raised hands. So let's thank Maria again for this fantastic talk. Thank you very much.